Hello ladies and gentlemen, today I'm going to tell you guys all the details that you need to know if you want to learn about the Lambert W function. And I'm going to do so by comparing the Lambert W function, which is also called the product log, with something that we know much better, which is of course the natural log. So have a look here. First, let me review what the natural log is all about. I'm not going to give you guys the integral definition for it, but rather let's just take a look at the equation. E to the x is equal to 2, for example. How do we solve it? Well, just take the ln on both sides, because this way, the left-hand side will just be x, and we can just write down x is equal to ln of 2. That's it. And the ln right here is exactly what we call the natural log function. And now the question is, how do we compute ln of 2? Well, either you can use your calculator, but if your calculator does not have a ln button or a log button, just buy another one. Well, if your calculator does not work, for example, we will have to do some approximation for it, right? And the approximation that we are going to do is using the Newton's method, because we're trying to solve the equation right here. So let me remind you guys how this works. And I am going to also be using this to talk about how to approximate the value for Lambert W function. So the Newton's method says, first, you need to have the equation right here, right? E to the x is equal to 2, but you want to have one side to be 0, so minus 2 on both sides. So e to the x minus 2 is equal to 0. Then you can define this to be your function. So I'm going to say let f of x to be e to the x minus 2. And you also need your derivative, and the derivative of this is just e to the x. So far, so good. Now the formula is xn plus 1. This right here is equal to the previous x value minus the function at the previous x value divided by the derivative at the previous x value. And what you have to do is, starting with the initial guess. Well, right here, I'm just going to say I will take x1 to be 1. Why? Because I'm looking at this as e to the first power, which is about 2.718, and then minus 2, pretty good, right? Not really, but you get the idea. You can also start with 0, etc., etc. And then you can just go ahead and do x2, which you just put 1 in here and here and here. So you have 1 minus f of 1 is just this, which is e to the first power minus 2, over, you're plugging 1 into here then, right? E to the first, and so on, so on, so on. And if you do it enough time, you will see that this value is going to converge to 0.6931, so on, so on, so on. And that's just how you can compute ln2, which is about 0.6931, right? Now, with that being said, what good does this do to help us understand the Lambert W function? Well, let's look at the equation. What if we have e to the x, but we have another x in front? Still, let's make this equal to 2. In this case, what do we do then? Well, we can just take the w on both sides. And this right here is just a notation for the Lambert W function. Again, it's called the product log as well. This is going to help us to just get the x on the left-hand side, which is really weird, right? Because you see the x here and also the x here, but yes, it does reduce out to just be x. And in here, we could just write x is equal to w of 2, just like your text form. Yeah. Anyway, though, this w, it's called the product log as well. So you can see how similar this and that are, right? Now the question is, how do we compute w of 2? Well, in this case, you really have to use a more advanced computer program such as Wolfram Alpha. You can just enter w of 2, and that will give you the value, or you can also enter product log of 2. But if you just have a simple calculator, most of the calculator does not have this function built in. So in that case, you will have to use the Newton's method, just like what we did over there. So I will give you guys a quick run through for this right here as well. Again, we'll be using the Newton's method right here. By Newton's method, because this is one of the most asked questions on my previous Lambert W function video. How do we compute w of 2 then, right? You can ask the accountant, but no, just no. Anyway, again, start with the equation. X e to the x is equal to 2, so minus 2 on both sides. X e to the x minus 2 is equal to 0. then define this part to be your function. So we have f of x is equal to x e to the x minus 2. And then we also need our derivative. Have a look. This right here, we need the product log. We need the product rule for the derivative. First one times the derivative second one plus the second one times the derivative first one, which is 1. So this is the derivative. Then again, use the Newton's method, which is this right here. And I'm not going to write down all the bunch of numbers, but here I will also tell you, if you take x1 to be 1, this will work out pretty well because I did it already. And x2 here we'll just do 1 minus, put a 1 in here and here, so we have 1 e to the 1 minus 2 over 1 in here, so we have 1 e1 plus e to the first. So get the value, we'll get a crazy decimal number right here, and then just keep plugging, right? Just keep going. And if you do it enough time, you will see that procedure is going to converge to 0.8526. So this will tell you W of 2 is approximately 0.8526. So hopefully this right here answers the question that how we can compute W of 2. So that's the first part. But of course, when we are talking about a new function, we should also talk about its domain, also in its range, right? So I'm going to do that by comparing the Lambert W function with the natural log, the ln function. So this is a legitimate function. It's not just like we want to use a new symbol to help us out with like weird equations. But anyway, part 3. What exactly did the ln function do for us? Well, if you have the original function f of x, let's say that's equal to x. We know this right here, that it's inverse. So let me write down the notation. This is exactly the natural log of x, right? Now, let me remind you guys the graph for e to the x and also ln x. E to the x, it needs no introduction. It looks like this. Cool. And if you look at the picture, let's talk about the domain. It's just all real numbers, so I'll put it as negative infinity to positive infinity. And the range is from 0 to infinity. And notice e to the x is always increasing, so it does have a very nice inverse, which is just that. And if you just do the reflection about y is equal to x, you can get a graph for ln x. And the cool thing about this is that the domain for the ln x is precisely the range of the original. So you know it's just going to go from 0 to infinity. Likewise, the range of the inverse function is precisely the domain of the original, which is that, negative infinity to positive infinity. Just like this. Pretty cool, huh? Now, two important properties. When we compose them, now this is what we used earlier. Suppose I put this right here, we will get e to the ln x power. What do we get? Well, this is just going to be x. However, you have to make sure that this is only true for x is greater than or equal to 0 or bigger. Well, actually, we cannot include 0, so when x is greater than 0. Because we have the ln x, we have to refer to the domain of the ln x. And if you look at this, you put it here, we have ln of e to the x. Well, this is another composition, and here you will still get x back. But this time, we are looking at e to the x. The domain is negative infinity to infinity. So this right here will be true for all x values. Right? Really cool, huh? Now, number 4 right here. It's the time for us to talk about the Lambert W function. Suppose we have f of x is x e to the x. And you guess it. The inverse, which is exactly what we use, is just the w of x. And this right here is just a notation for the Lambert W function, or also called the product log. Well, here's the deal. Suppose, again, I give you the graph for x times e to the x. The problem for that is that you will see the function is not always increasing. It's like this, and then it's going to go like this. So for this portion of the graph, it's decreasing, right? This is not going to give us the nice inverse. So what we have to do is find out the minimum right here, and that happens when x is equal to -1. You can just do the first derivative test if you would like, etc., etc. And then the corresponding minimum value for the function is at -1/e. So let me just put that down right here for you guys. So have a look. In this case though, the domain to have the inverse for this function will be going from -1, including -1, and then to infinity, and then the corresponding range will be going from -1/e to infinity. Now, with that being said, we know for the Lambert W function, we just have to reflect this part, right? Again, about the diagonal line right here. So we will actually have to start at -1/e. Sorry about my drawing right here. And then the minimum value here is actually at -1. So the picture is going to look like this. So this is the graph for w of x, and this is for x e to the x. Now, the beauty of all this is that the domain for w of x is just the range of that, which we talk about it, -1/e to infinity. And then the range for w of x is just that, -1 to infinity. And again, we're just keeping everything real right here. So this right here will give you the real values. Yep. So that's about all. Now, again, two important properties. If we compose them, right? First thing first, if I put w of x in here and here, well, it looks like we will have w of x times e to the w of x, like so. When you have this, yes, you will get the x back, but here you have to be careful that this is only for x is greater than or equal to. Pay attention to the domain for the w of x, which is -1/e. Domain matters, right? So this is true if x is greater than or equal to -1/e. And the other way, if you put this right here, it looks like we will have w of x. Oops, wrong color. Put this in here, we get w of x times e to the x power, and here we will get x back as well, but here just refer to the domain of x to the e to the x, the domain to have inverse. But anyway, this right here will be true if x is greater than or equal to -1, like this, right? Really cool. And once you know about the Lambert W function, you actually get to solve a lot more equations, and your life will be happier, right? I promise you. So this is pretty much it. Now let's talk about how we can compute some nice values for natural log and also for the product log. Yep. Of course, you have the calculator for the natural log, but let's not use a calculator for the following. So, number 5, nice values for natural log. So here are just the nice values. Actually, let me just put this on here. Number 5 for lnx. I'm going to give you guys a couple examples, right? So I'm not going to write down the first one. As I said, it's part 8. How do you compute ln of 1? Let me put the 1 inside in red. Right? ln 1. And then also let me give you part B, ln of 1/e. And then C, ln of square root of e. So this right here will give you some nice values. Remember, if you have a nice number inside, it might not give you a nice value. ln2, it's not a nice value, right? But this right here will be. And the way to do it is use the property that we mentioned it before, which again is that, remember, when we have w of, actually, sorry, this is not w. When we have ln of e to the x, this right here will give you the x back, right? So that's the key deal. Now, here we have ln. For 1, e to what power will be 1? E to the 0th power will be 1. So we can write this as e to the 0th power. And this way, you see, they cancel out, and you just get 0. And this right here is the answer. Second one, we can look at 1/e as e to the -1 power. And you see the answer is just going to be -1, right? Very nice. And then the third one, the square root, it's the same as 1/2 power. So we can look at this as ln of e to the 1/2 power. And when we do that, we can see the answer is just 1/2. So again, we use that property to help us compute the nice values for natural log functions. And I'm going to give you guys another one, but I'm not going to do it for now. Part D, let's compute some complex values. Maybe I'll do this later, or maybe at the end. Let's look at ln of I. If you know what it is already, you can just try to figure it out, or just leave a comment down below for now. But anyway, I'm going to keep everything real for now, yeah? So, for number 6, nice values for w of x. I'm going to give you guys some examples. First one, let's say if you want to compute w of 0, right? And then second one, I will say let's do w of -1/e. And again, all these questions, if you want to end up with nice values, you have to pick nice values inside in the first place, right? Anyway, part C, w of 2 ln 2, right? So you want to pause the video and try to figure this out? Right, cool, I assume you did that. Now, have a look. This is the thought process. Note, again, we have to use the idea that w of, if we have x, e to the x power, right, this is the property that I mentioned earlier. This right here will give you x. This and that, they have to be the same. And if you have watched my other videos already, you know I usually like to draw fish right here. And the fish is actually from alpha. So if you guys have been wondering why I draw fish all the time, it's because alpha, but it's also kind of cute. Anyway though, here we have w of 0. So how can we write 0 in this form? Well, have a look. It's just w of 0 times e to the 0's power. Can we do that? Yes. In this case, it's just equal to 0. So the answer is 0. Done deal. Next one, w, and then we have this negative, so let me just put it as -1. Let me emphasize the -1. In the meantime, 1/e is the same as e to the -1. And do you guys see it? -1 match, so the answer is just -1. Very nice. For this one, it's slightly trickier. I will have to use the blue marker. We have to pay attention to the number 2 right here. Let me first write down the w again. So we have w here. I'm going to keep the ln2 in red right here. So here we have ln2. But for this 2 in blue, we have to look at the 2 as e to the ln2. Again, because we have to introduce the e, and we have to make sure this and that match so we can get this fish back. When we do that right here, you'll see the ln2, they match exactly. So the answer to this is precisely ln2, which is, I would say it's pretty nice, right? It's a pretty nice answer for that. Yeah, cool. Now, you can also generalize this. You can say w of 3 ln3, etc., etc., but I will leave that to you. And let's also talk about part D. What if we have w of a weirder number, let's say -pi/2. For now, you guys can pause the video and try to think about if you can figure it out and figure this out, and leave a comment down below and let me know. And I wonder if I should do it right now. I don't know. Maybe not. I want to keep everything real in this video, so maybe next video, right? So that's the first 6 part, and now I'm going to show you guys how to solve some equations. And later on, I'll also show you guys the derivative and also integrals. So keep watching. Number 7, I'm going to solve 2 equations for you guys. All right, first thing first. Suppose I want you guys to solve x. No, let's do this one first. And yes, I'm going to do the one on a t-shirt, but later on, yeah? Anyway, let's solve e to the x plus e to the negative x. Let's say this is equal to 1. Let's actually make it equal to minus. If that was a plus, x would be just equal to 0, and that's kind of boring, so better equation right here. Do we need to use the Lambert W function or no? Well, have a look right here. This is how we can solve it. Ready? First, notice that we have e to the negative x power, so I'm just going to multiply everybody by e to the positive x. So you can see here, we get e to the x times e to the x, which is e to the x squared. So I'm going to write this as e to the x squared. Yeah. And then this times that is just going to be minus 1. So I'm going to write it down like this. And then 1 times e to the x is just e to the x. But I will bring that to the left hand side. So we have minus e to the x. Like this. And you can see that this right here is actually an equation in the quadratic form. So you can use the quadratic formula. In terms of e to the x though. So we have e to the x, that's equal to negative b, which is negative 1 right here, plus or minus, open the square root, b squared, which is negative 1 squared, minus 4ac. A is 1, c is negative 1. And then all divided by 2 times a, which is 1. So that's pretty much all we have. And now you will see e to the x is equal to 1 plus or minus. This inside will be 5, so we have square root of 5 right here, all over 2. Well, do we take the plus, or do we take the minus, or do we take both? Well, we just take the plus because e to the x has to be positive, right? Again, keep everything real. And notice 1 plus square root of 5 over 2. It's a special number, isn't it? Yes, the golden ratio. So that's why I picked this equation. Anyway though, once we have e to the x by itself, we can then just take the ln on both sides. You guys all know this already, and they cancel. And ladies and gentlemen, x is equal to natural log of the golden ratio, 1 plus square root of 5 over 2. Pretty cool, huh? All right, let me see if I can solve another equation right here, number 8. Let's solve this equation. This time, I'm going to change it a little bit. Let's look at what if we have x plus e to the x. And let's say this is equal to 2. How can we solve this equation then? Well, earlier you see we have e to the x and also e to the negative x, but somehow we were able to avoid using the Lambert W function. But if you have a power function like x to the first power and then something else with e to the some power, your best bet is somehow try to use the Lambert W function, right? Well, this is how we can do it. Have a look right here. Remember, we really need to have w of the fish, right, times e to the same fish. We really need to have this form in order to get the fish back. We have this e to the x already. Well, what I'm going to do is look at this and look at that. I'll pretend both of them are the exponent, because if I put e to the power and also e to the power, I will produce e to the x. In the meantime, the e to the x will be in the exponent right here as well. Have a look. This right here, because we have the sum, this is in the exponent, so this right here becomes e to the x, this part is just e to the x, times e, right, to the e to the x, isn't it? Yes, it is. And you see this and that are the same now, and the right hand side is equal to e to the second power. So when we have this situation, we are in business because we can just take the Lambert W function on both sides. So put the w here, put the w here. On the left hand side, we'll just get this back right here. So I'll write it down e to the x, and this is equal to w of e to the second power. Well, we have this now. How do we solve for x? You see, natural log and product log, they will work together in here. We just take the ln on both sides then. So, ladies and gentlemen, here x is equal to ln of w of e to the second power. Oh my god, I have the exponent here, I have the Lambert W function, I have the natural log right here. How cool is this? Now, I will show you guys how to solve this equation right here. So, number 9. I wrote such a big, I used such a big space for the number 7, but anyway, number 9 right here. So have a look. How do we solve the equation? X to the x power is equal to 2 then. Want to pause the video and give this a try? Well, have a look right here. Hopefully you guys actually tried it. I will first take the natural log on both sides so that we can bring the power to the front, and then we'll just get x times ln x. That will be equal to ln 2. Very nice. And again, we need to have this situation here. We have the ln x right here already. Well, this is very similar to the w of 2 ln 2 question earlier. Let's look at this x right here in red. I'm going to put this down right here first. But this x in red, we are going to write it as e to the ln x power. Aha! And this is equal to ln 2. This and that match. So it's the time for us to take the Lambert W function on both sides. And we will get just ln x right here. And that's equal to w of ln 2. Well, what do we do next? Here, we can pretend this and that are the exponents. So we do e to this power, e to that power. They cancel. We will just get x by itself. X is equal to e to the w of ln 2. Wow. Yeah, so e w ln 2, ln w e 2. Really cool, huh? Yeah, and that's exactly what I have on my shirt. All right, so number 9 is about how to solve this equation. Now, I think we should be good with the algebra part with the Lambert W function. Of course, it can be pretty tricky sometimes. However, though, let's just move to some calculus, right? So, number 10 and later will be calculus. I'll show you guys the derivative and integrals. That will be it. So, have a look. Number 10, let's find the derivative. Of course, not just the Lambert W function. Let's find the derivative for the ln x first. How do we do this? One easy way is just let y equal to ln x. Once we have this, we know this is the same as saying e to the y is equal to x. And then we can do implicit differentiation. So I put down d dx over there, and then the derivative of e to the y is still just e to the y, and then we multiply by the derivative of y because of the chain rule, so we get dy dx. And the right hand side, the derivative of x is just equal to 1. So you see, dy dx is just nicely equal to 1 over e to the y. But what's e to the y? E to the y is of course just x, so all in all we just get 1 over x. That's the answer for the derivative of 1. That's the derivative of ln of x. Nice. Now, let's look at what if we have to differentiate the Lambert W function. You guys see why I show you guys this? Yes, because we can do the same strategy. First off, I'm going to say let y equal to w of x. And then I will take the inverse on both sides, which is just the original, which is going to be y e to the y, it's going to be x, right? You see, if we have this, take the w on both sides, we'll get w here, and then we have w of x. Now, with that being said, we can then just do the implicit differentiation. Here we need to use the product rule for derivative. Well, first function is y times the derivative second, which is e to the y, but multiplied by the derivative right here because of the chain rule. And then we add the second function, e to the y, times the derivative of the first, which is, again, dy dx. And then on the right-hand side, the derivative x is just equal to 1. Well, both of them have dy dx, so we can factor that out. So we just have this plus that in the parentheses. We can divide that on both sides. So, ladies and gentlemen, dy dx is equal to 1 over ye to the y plus e to the y. Can we simplify this a little bit? Sure, yes, of course. Refer this right here, right? Look at this. This is just equal to x. Pretty nice. How about e to the y? Well, y is equal to w of x. So if you would like, you can look at the y as w of x. First answer, if you prefer, you can write it as 1 over x plus e to the w of x. But notice this and that, they do not cancel out, okay? So you just have to keep it like that. So this is one way to write the answer, but another way to write the answer is the following. If you look at e to the y and refer to here, we know y e to the y is equal to x. So we can divide the y on both sides. We have e to the y is equal to w over y, but y is equal to what? Y is equal to w of x. So this is the same as x over this y becomes w of x. So I can also write this down as 1 over x right here, and then plus x over w of x. And of course, we end up with a complex fraction, which is not preferred. So let's multiply the top and bottom by w of x. So we have w of x on the top over, let me also factor out the x if you don't mind. So we have x times, and the inside is just going to be w of x plus 1. Yeah, so either this or that, up to you, right? So that's how you differentiate the Lambert W function. And now, of course, let's move on to how to integrate the Lambert W function. So have a look. Good. How are you guys doing? I don't know how long this video is already. And Happy New Year, everybody. Perhaps this is going to be my first upload in 2021 for my usual channel. All right, integrals. That was 10, 11, now it's 12. So integral, of course, don't forget about the natural log. How do we do this? Yes, integration by parts. But no, I am not going to show you guys that. Why? For the benefit of integrating the Lambert W function, I will have to show you guys something else that's cooler, right? So have a look right here, ladies and gentlemen. Right here, I'm going to put this down right here, right? This is all I need. So note, because remember, the ln x, it's actually the inverse of e to the x. So it's an inverse function, right? So what if you want to integrate an inverse function in general? Well, let me just write this down right here for you guys. Suppose if you integrate the original function, I'm just going to write it as capital F of x. So this is just the antiderivative for the little f. Then in that case, if you want to integrate this guy's inverse, this is a really nice formula for you guys. But I'm not going to just give you guys a formula. I will show you guys how to derive that real quick. So this is going to be good for all. So how do we take up this? Well, first, let's do a u sub. Let u equal to the inverse function. And you know this will work if you let u equal to ln x as well. So this is really legit. What I do next is, well, we still have to get the dx, right? So I will take the original on both sides. This implies x is equal to f of u. And then I will differentiate both sides. So I get dx being equal to, I will write it as f prime of u. So f prime of u. And then du. So now we can take this integral to the u world. Have a look. This becomes the integral. This guy is the u. And then this guy is this, which is f prime of u du. And in fact, it's usually easier if you do u sub first when you have the inverse function before you do integration by parts. Now, to take up this, yes, we have to use integration by parts. Of course, I will show you guys the DI method. Well, this right here is a derivative, so I'm not going to differentiate that. I can actually just integrate that, which is going to be really nice. And let me have more space right here, so I'll put the D right here, slightly closer. In the meantime, I will just go ahead and differentiate u. Differentiating u in the u world, we get 1. Integrating f prime of u, we just get f of u, right? F prime, integrate that, we get f of u. So now, when we multiply this and that, that's the first part of the answer. So we have u, f of u. And then remember, when we multiply this row, this is still going to be an integral, so we have to minus, and this is 1 times f of u, so we just have f of u. Of course, we are still in the u world. Well, let's see. What's u right here? This u is precisely our inverse, right? F inverse of x. And what's f of u? F of u is just equal to x, so I'm going to say this is multiplied by x, like so. And then minus integral of f of u is what? Well, I gave you guys a notation already. This right here is just going to be capital F of x. So this is just going to be capital F of u, right? This is that, the entire derivative for the original, and we're trying to integrate the inverse. Last step, well, usually we like to put the x in front, and then f inverse, and then minus, this right here is capital F, and what's u right here? U is f inverse. Yes, this is very confusing, but that's why I gave you guys that, because I want to do an example with you guys first. This right here is what we have. It's a formula, but I think I will still put a plus c. Doesn't really matter though, because, well, I'll just put the, because f is an entire derivative anyway, put a plus c right here anyway. All right, how can we utilize this to integrate L and X? First thing first, I'm just going to denote for you guys. Here, our inverse function is precisely L and X, right? That's our function, that's inverse. We know the original will be e to the x. And then we know capital F of x, which is just the integral of that, is going to be still e to the x. So if you integrate both sides, you get that e to the x, right? If you want me to put on the dx, I will do it for you. No need for plus c right here though. Now, all we have to do is actually just a one-liner. This right here, by using this formula, we will have x times the inverse of f. So it's just x times the inverse of f, which is just going to be x times ln x. And then minus, well, we will have to enter the inverse function into the capital F. This is the inverse function. We will have to enter this into the capital F right here. So we actually get e to the power, of course they cancel. So finally, ladies and gentlemen, is x times ln x minus x, and finally right here, I will put on the plus c, and this right here is it. Have a look. Really powerful, isn't it? All right, the last thing I want to show you, of course, it's perhaps the grand prize of the day, is the integral of the Lambert W function. So, number 13, let's look at the integral of the Lambert W function. Well, let's come up with the similar notations. First, I'll write f inverse is our w of x. As we mentioned earlier, this is the inverse function. Inverse function of what? Well, the inverse function for x, e to the x, right? Now, I also need to have the capital F. So in that case, we just have to integrate. So we can actually get a capital F right here. Well, here you do integration by parts, and I will tell you the answer is actually just x e to the x minus x, right? Just use integration by parts and you will get the answer for that. Now we are ready to just use this. So this is going to be f times the inverse, so x times the inverse, so we have x times the inverse, so x times w of x. That's the first part of the answer. How cool is that? Next, minus. we have to put the inverse into the big F. So we will have to put this into all the x right here, right? It has two parts, so let me open the parentheses. So first I will have to enter we will have to enter w of x right here. And don't just write w, you should technically write w of x. Yeah, and then e, and then w of x. And then minus w of x. That's pretty much it. That's pretty much it. No, you know what? I lied. I lied. This is not just minus. Wait, hold on. I think I should still show it. No, let me integrate this a little bit for you guys. All right, so do the d and the I. I'm going to differentiate x and integrate e to the x, and then we have we get 1, 0, and then e to the x. Sorry, I remember the antiderivative wrong right here. That's why the answer is too nice right here. All right, so integrating this, you multiply this and that, multiply this and that. So first is x times e to the x, and then minus e to the x. And that's it, because you have the 0 in the d column. So let me just do this again. We will have to enter w of x into here and here, and also here. So we have to minus e to the w of x, like that, right? Well, w of x times e to the w of x, can we simplify that? Yes, because the whole thing is nicely equal to just x, right? It's just equal to x. So the first answer that you can provide is just x w of x, and then minus x, and then minus e to the w of x. And then right here, I'll put down the plus c for you guys. So this right here is the it's an answer for it. But if you want to end up with the answer on Wikipedia, then you can do the following. And that's where I get all my information. Now, most of my information, of course, I'm adding some of my own presentation as well. But if you want to end up with the answer on Wikipedia, they just fix this guy right here. So another thing that you can see is, we know w of x, e to the w of x, this is equal to x, right? We can divide the w of x on both sides. So this is equivalent to say, e to the w of x equals x over w of x. So they just replace that with this. So finally, I will also give you guys the answer, x w of x minus x minus, I'm sorry, minus of course is a plus. And then here we have x over w of x. That's it. Put a plus c like that. All right. Really cool, huh? So of course, you know, I will of course do the complex numbers for you guys as well. So after the calculus, you can learn some complex analysis. Well, after this, have a look. 2 more things. That's it, right? And hopefully after this video, you guys can really have a better understanding of how the basics of the Lambert W function works. Right? All right, so that was number 13. Now let's look at number 14. Here, let's look at how to do ln I. Well, for this right here, look at I. We will have to change this into the polar form. To do so, look at the complex plane real quick. And we know I is right here. And we need to have the distance from the origin to I, which is just from here to here. And that distance is just equal to 1. And we also need to know the angle, which is just from here to here. And the angle is just pi over 2. But the truth is, you can keep rotating, right? Because you can just, keep rotating, just keep adding the 2 pi, etc., etc. So if you do that, you can actually get infinitely many answers for this. So technically, put down plus 2 n pi, and n is just an integer, right? But anyway, though, look at this right here. We have ln, and I is equal to r e I theta. R is 1, so just have e, and then we have the I, and the theta, if you would like, you can just put down pi over 2. That's the first answer, the principal value, pretty much. So in the end, this and that cancel, you pretty much just get I pi over 2, like this. But for the people who are about to comment that I should find out all the solutions, this is for you guys. Here, again, we should technically add 2 pi, right? So right here, this and that will still cancel, so you just put on plus 2 pi. Yeah, just like that. And I'm going to leave this to you guys to simplify. No, I will simplify it for you guys. Multiply the bottom and the top by 2. So we have 4n. So let me see. All right, 4n plus 1, then factor out the pi, yeah? And then divided by 2, yeah? And then put the I right here, yeah? And then the n is just a integer, so maybe denote this right here, yeah? So you have infinitely many answers for L and I. So this right here is it. Okay. And for the last question, I cannot find out all the values for you guys. So let me just tell you guys that first. Anyway, W of negative pi over 2. How do we do this? Well, we need to have the fish times e to the same fish, right? So we need to introduce the e. The way to do it is have a look right here for the negative. What's negative? Of course, positive times negative is negative, but that's not complex analysis. We know I times I is equal to negative, right? So this right here, we can look at this as W of pi over 2, and then let's just write down I times I. So let me put down the I in black first, times I. That's of course the same as negative 1, no problem on that. Well, in this case, W, here we have pi over 2i already. For the I, hey, we saw that it was e to the I pi over 2, isn't it? So we can write the I right here as e to the pi over 2i. Just put the I at the end, which is the same thing. But you see, here, you really have to be really careful with the angles. Let me just use the principle for you for the I right here for the complex form. The reason is because now this and that are the same. So the final answer is just going to be nicely equal to pi over 2 I. And of course, I like that very much. Hopefully, you guys like this as well. Right? So all 15 little points right here for you guys for the Lambert W function. If you have any questions, leave a comment down below. Let me know. If you're new to my channel, please consider to subscribe. Thank you guys so much. Have a happy new year. Best wish to you guys. That's it.